Welcome to the flock. This is part 3 of an acid-base series. In this lesson, you'll learn how to calculate for pOH, pH, and concentrations of hydroxide or hydronium ions, according to all of these equations. Let's dive into some acid-base calculations. Stick around to see how it's done. For the past 2 lessons, we've been talking a lot about this pH, but what do you think the P and the H even stand for? We're literally thinking of the P as the power and the H as hydrogen. However, let's be real. Mathematically, the P is equivalent to negative log. Remember that the pH scale is based on a logarithmic scale. So the P itself is indicating negative log. And in chemistry, when we put brackets around anything, we're talking about molarity, concentration, moles per liter of solution. Molarity is moles per liter of solution. So for example, if you were to see bracket H3O plus hydronium ion, that means the concentration of hydronium ion. Or bracket OH hydroxide ion, that would mean the concentration of hydroxide ion. Ta-da! So then how can we relate this whole pH thing, the power of hydrogen, to concentration? Well, remember that for something to be neutral, like water, it has to have equal parts hydrogen ion or hydronium ion to equal parts hydroxide ions in solution. So pH is literally the concentration of the amount of hydronium ion to the amount of hydroxide ion in solution. So if we were going to break up the pH mathematically, the P, as we stated, is a negative log, and the H is the concentration of hydrogen ions, or hydronium ions, H3O+. Therefore, pH as a mathematical setup is literally equal to negative log times the concentration of protons, hydronium ions, in solution. And that's where our very first formula comes from in terms of pH. So if we need to find pH using a concentration of an acid, in other words, the concentration of the acid is given, we would use pH is equal to negative log times H3O+. That would be the concentration we were given. We can take this same equation and rearrange it. Say we're trying to find the concentration of the acid and we're given the pH. Well, as long as we rearrange the equation and make it look like this, then we can just plug in the given pH and solve for the concentration of the acid. Now, if we're talking about bases, we're going to use something called pOH. That's going to be the negative log of the hydroxide ion concentration in solution. We're going to use a very similar setup, except it's going to say pOH for the base. And it'll be the negative log times the hydroxide ion concentration. Just like before, we can rearrange this equation since we know that log is base 10 and undo the log in order to solve for the concentration of the base if we're given the pOH. As follows: hydroxide ion concentration is equivalent to 10 raised to the negative pOH. In part 1 of this series, we talked about how water has equivalent parts of H3O plus at 1 times 10 to the negative 7 concentration, and equivalent parts of OH minus at 1 times 10 to the negative 7 concentration. Because of this, we can say that pH plus pOH should be equivalent to 14, because 7 plus 7 is 14, and that's the range of our pH scale, 0 to 14. In case you needed a refresher on how I rearranged those equations using logs and base 10, first we would move the negative sign over, and now we would have negative pH equal to log times the concentration of the acid. In order to undo the log, we need to base 10 it. So that would cancel out the log on this side and give us 10 raised to the negative pH on the other side. And now we can clearly see how the concentration of acid would be equivalent to 10 raised to the negative pH. And of course, the same methodology would be used to find the concentration of base, 10 raised to the negative pOH. So let's go ahead and give one of these calculations a try. If the aqua hydrate water has a hydronium ion concentration of 3.16 times 10 to the negative 10, what's the pH of this water? So we're obviously going to need to use the equation setup of pH equal to negative log times hydronium ion concentration. We were given the hydronium ion concentration right here, so we're just going to plug that in there. pH is equal to negative log times 3.16 times 10 to the negative 10. You'll need a scientific calculator for this. On your scientific calculator, the first thing you want to press is the negative down here. Negative, and then you want to press log right here. That'll give you a negative log on your screen in a parenthesis. Inside those parentheses, you're going to write 3.16 second EE for the shortcut for times 10 to the, and then another negative 10. Last thing you need to do is close your parenthesis here and hit enter. We see that our pH is 9.5. That means that this water would be pretty basic. What is the pOH of this water then? Well, we have another equation we can use. pH plus pOH equals 14. We already know the pH now. We solved that. It's 9.5. So to solve for pOH, we can just take pH from this side and subtract it from the other side. Then what we get is pOH equals 14 minus 9.5, what we already calculated. And we see that our pOH value then is 4.5. Lastly, what is the concentration of hydroxide ion? Well, we have the pOH and we have the pH. We need to solve for the hydroxide ion concentration. Remember, when we're talking about concentration, think brackets. So hydroxide ion would be brackets OH minus. We need the equation that solves for bracket OH minus. That happens to be 10 raised to the negative pOH. We're just going to take our pOH from before, 4.5, and plug it in there. In our calculator, 10 raised to the negative 4.5 gives us a value of 3.16 times 10 to the negative 5 molar. Remember, this is a concentration, so don't forget your units of molarity. Before I have you jump in and try one on your own, here's some basic steps to use when you're calculating for pH and pOH. You'll most likely be using all of the equations, at least 2, for every problem in acid-base calculations. Step 1. Identify the acids and bases in the balanced chemical equation, if there is one. Step 2. Identify the givens of the problem and label them accordingly. So identify what the question is even asking of you. Is it asking for a concentration of hydronium or hydroxide? Is it asking for pH or pOH? Step 3, figure out which equation to use and plug and chug into the applicable acid-base equation from the list I gave you. All right, it's time for you to try this acid-base calculation. My favorite flower in the whole world are called hydrangeas. Hydrangeas are the chemist's flower because they can change the color of their petals based on the pH of the soil they're grown in. If you want blue flowers, you need to grow hydrangeas in acidic soil, pH of 5.5 or lower. If you want pink flowers, you would need to plant them in neutral to alkaline soils, usually pH 6.5 or higher. And if you really want purple flowers, you're going to plant them in soil that's between pH of 5.5 and 6.5. So let's say the soil in your garden had a hydronium ion concentration of 3.16 times 10 to the negative 5. What would be the pH of that soil? What's the pOH? And what's the hydroxide ion concentration of your soil? Go ahead and figure out what the color of your hydrangea flowers would be in your garden. Ready, go! You would have very pretty blue flowers at a pH of 4.5. Hopefully these are the answers you got. Let's try another one. In the series Breaking Bad, Walter White dissolved a whole human body with hydrofluoric acid, which is a weak acid, by the way. However, to dissolve a human body quickly, minus the bones that is, 18 molar sodium hydroxide, NaOH, is actually a better alternative, but you didn't hear it from me. Assuming that the pH of 18 molar NaOH is roughly 13.98, what would be the pOH of this NaOH solution? What would be the hydronium ion concentration? And what is the hydroxide ion concentration? Go ahead and pause the video here and see if you can figure it out. Notice that the hydronium ion concentration here is really small. 1 times 10 to the negative 14. Guys, that's like a lot of zeros in front of a 1 as a decimal. That's a really tiny concentration. There's hardly any acid in that solution. However, there is 0.95 molar hydroxide ion concentration. It's almost a 1 molar solution of straight up OH hydroxide ions. That's really basic. Let's apply these calculations to some real-world examples. Acid rain. If we're gonna look at this map of the United States, where does acid rain appear to be the worst? Hopefully you see, based off of this field pH down here in the corner, that the worst is going to be in this red-orange zone. And clearly the East Coast is kind of plagued with this red-orange zone in terms of acid rain. Why is that the case? Why is there so much acid rain on the East Coast in comparison to the entire West Coast? In part, acid rain forms due to coal and other industrial processes, which are very prominent on the East Coast. These create many different toxic gases in our atmosphere, including SO2. SO2 gets converted to SO3 in the atmosphere after coal is burned at power plants. And as you hopefully know, there is water in our atmosphere. That's kind of what clouds are made out of. So SO3 reacts with water to form sulfuric acid, H2SO4, in the sky. And then of course that has to go somewhere. It rains down as acid rain. Let's try and see if we can determine the hydronium ion concentration if the pH of acid rain is typically around 4.4 on the East Coast in the United States. We have our equation, pH equals negative log times the hydronium ion concentration. We know that the pH is 4.4, so let's plug in 4.4 and rearrange this equation just as we did before. We would move the negative over and have the base 10, and that would be equivalent to 10 raised to negative 4.4 equal to our hydronium ion concentration. Or you could have just plugged and chugged from the equations I gave you. This ends up equaling 3.98 times 10 to the negative 5 moles per liter. Now that might not seem like a lot, but that's still enough to start dissolving statues from our history and to destroy wildlife, because turns out they don't like having acid rained on them. Because it turns out that trees actually don't like being covered in acid in comparison to water. Go ahead and give this one a try. An acid rain solution had a pOH of 7.6. What was the solution's pH? Pause the video here to solve this question. If 7 is neutral on our pH scale, we can clearly see that this acid rain is more acidic at 6.4. Now, seawater itself is slightly basic. It usually has a pH of 8.14. However, it's projected that the seawater should have a concentration of 1.58 times 10 to the negative 8 molar, or moles per liter, in the year 2094. Now this occurs because of CO2. As CO2 from the air enters our seawater, also known as a carbon sink, it makes the seawater more acidic, i.e. it drops the pH to a lower value. Don't believe me? Let me show you in this simple example. In these flasks, I have an indicator called red cabbage. You can see a previous video in my part 1 of acids and bases, how you can use cabbage water, just created from red cabbage leaves, as an indicator of pH. To this cabbage water, I'm just gonna add some water. Normal, purified water. Now granted, I don't have ocean water on hand, I don't have the exact salt water, but I think water will suffice in just demonstrating the difference. Now that I've added some water, I'm going to keep this one as my control flask, meaning I'm not going to blow air into it, and I am going to blow air into this flask, our test flask. Why am I blowing air into it? Well, when we breathe in oxygen, and we breathe out CO2. CO2 is the thing that acidifies the ocean water. So if I blow CO2 into this flask, we should see it change color and become more red as an indicator of acidity, according to the red cabbage water indicator in the water. Ready? Let's see what happens. Hopefully you can see the clear difference between the control flask, which is still purplish, and the one that I blew a bunch of CO2 into, which is now a pinkish color. It's become more acidic due to all of that CO2 addition. So what? So why is that a big deal? Well, shells in the ocean, which happen to house like a lot of organisms in the ocean, depend on calcium carbonate. That's the same stuff that makes up a chicken egg's shell. And calcium carbonate's the same thing that's in a seashell, or any of the shells that crabs and slugs and sea snails and all of those critters live inside of. So what happens to this eggshell if we soak it in acid? For example, let's soak it in some vinegar, which is just a household acid. I'm gonna let that soak for a couple days and show you what happens. But right away, you should see little bubbles forming on the outside of the eggshell. And as we know, bubbles indicate that a chemical reaction is occurring. While we wait for that egg to soak, let's work through this calculation together. Given this concentration of hydronium ion in the year 2094, let's try and determine what the pH of that hypothetical ocean water sample would be. We know that pH is equal to negative log of the concentration of hydronium ion, 1.58 times 10 to the negative 8. Plugging that into our calculator, we get a pH value of 7.8. Now what's the big deal? Isn't pH normally 7 for neutral? Isn't that a good thing? No, not necessarily here. Remember that ocean water, seawater, is normally a pH of 8.14. So to jump to 7.8 is a huge difference. Remember, the pH scale is based on a log scale. That's a 10-fold difference when you change from one pH to another. One step is a 10-fold change. Let that sink in. 8.14 to 7.8 isn't a full one step, but if 1 to 2 pH is a 10-fold change, this is still a drastic change in terms of the sea life that live in the ocean. And here you have it, folks. Just a mere 24 hours later, and the eggshell on this chicken egg has completely dissolved in the acetic acid vinegar. You can literally see how the eggshell is completely gone. You can actually see the egg yolk floating around in there, and this is squishy, held together by merely the membrane of the egg. Now this is the exact same chemical reaction that's occurring with seashells and with all of the shells made out of calcium carbonate, the same thing that the eggshell's made out of, when the ocean water becomes more acidic. This is a problem because if shellfish don't have shells to live in, that essentially means that they are sitting ducks for other predators to eat them and thus disrupt the entire ecosystem and food chain. Since a lot of the world depends on seafood for survival, that's kind of a big deal to interrupt the oceanic ecosystem. Before you move on to part 4 of this series, make sure you test your understanding of POH, pH, and concentration calculations. An acid rain solution has a POH of 8.2. What's the solution's pH? If you'd like to know the answer to this test yourself question, please comment below and I'll be happy to tell you if you got it right. In this lesson, we learned that P stands for power, just kidding, stands for negative log, and H stands for the hydronium ion concentration. Therefore, pH is literally equal to negative log times the hydronium ion concentration as our first equation. We can also rearrange that equation to solve for the concentration of hydronium ion by setting it equal to 10 raised to the negative pH. We can also solve for POH in two ways. If you were given pH, you could take pH plus POH equals 14 and subtract out the pH. Or POH can be set equal to negative log times the concentration of hydroxide ions. If you rearrange that same equation, you can solve for the concentration of hydroxide ions by taking base 10 raised to negative POH. For acid-base calculations, you'll likely use any 5 of those equations, or all 5 in fact, to solve for concentrations, pH or POH. In terms of acid and base calculations, if you'd like just a little bit more, check out part 4. I'll see you there.
No ducks, no glory.